Although linear programs are solvable in polynomial time, solving large sparse instances can be challenging in practice. For example, instances of basic LP relaxation of weighted CSP originating in computer vision may have millions of variables. To solve such LPs, the classical methods are not always suitable, if only for their superlinear space complexity. We propose an alternative approximate method which can have linear space complexity and is based on constraint propagation. Let us consider the following primal-dual pair. Note that any y feasible for the dual on the right is an upper bound on the common optimal value. By the well-known complementary slackness theorem, a dual feasible solution y is optimal if and only if there exists an x satisfying conditions 2, which can be seen as a system of linear equalities and inequalities in X. Suppose that we have an initial dual feasible solution. If the complementary slackness conditions are feasible, then it is optimal. If they are infeasible, we can construct an infeasibility certificate by Farkas lemma, which turns out to be a dual improving direction, using which we can improve the current y. Doing this iteratively, we obtain a better and better bound on the optimal value. This is well known in linear programming as the Primal-Dual method. Since checking feasibility of large systems of linear inequalities is costly, we propose to solve it by constraint propagation, which may however not always detect infeasibility. While constraint propagation in continuous variables is known, the novelty is in the fact that whenever we prove infeasibility by constraint propagation, we also construct a certificate of infeasibility in the sense of Farkas lemma, which provides us a dual improving direction. If no infeasibility is detected, we terminate. Note that we may not obtain an optimal solution, but only an upper bound. We show that this approach is a generalization of virtual R consistency algorithm, which approximately optimizes the basic LP relaxation of weighted CSP. We illustrate the approach on the LP relaxation of weighted maxat, for which we define the propagation rules and a memory-efficient way of calculating the infeasibility certificate. Provided bounds are exact for instances of weighted max2 sat and non-tractable subclasses. In other cases, the bounds are often not far from the optima of the LP based on experiments using a public dataset. Such approach is in theory applicable to any LP, but the quality of the obtained bounds critically depends on problem structure and strength of the propagation rules. We are now going to present our approach in detail. Let us now focus on testing feasibility of the complementary slackness conditions. For simplicity, we assume that the conditions are given as a system of linear inequalities where A and B are different than previously. The task is to decide feasibility of the system and, if it is infeasible, provide a certificate of infeasibility. Such certificate has only polynomial size in this case. Of course, this can be done by linear programming or by Fourier-Motzkin elimination, but this can be computationally challenging for large instances. The main idea of constraint propagation in a CSP is that from a given set of relations, we generate a new relation which is implied by the previous relations and add it to the set. We repeat this until either we reach a contradiction or no more inference rules are applicable. While in general CSP, it is hard to decide whether a given set of relations implies another given relation, the situation is much easier if the relations are linear inequalities over the reals. In detail, the logic of linear inequalities over real numbers is exactly described by Farkas lemma, which says that a system of linear inequalities is infeasible if and only if there exists a non-negative combination of the inequalities which is contradictory, which happens if and only if there exists vector y satisfying the shown conditions. Such y is a certificate of infeasibility. There also exists a variant of this lemma for inference, called a fine Farkas lemma. A system of linear inequalities implies a given inequality if and only if it is implied by a non-negative combination of the original inequalities, which happens if and only if there exists a vector y with the shown properties which encodes the inequality and will be called the cause vector of the implied inequality. In our setting, constraint propagation in a set of linear inequalities will consist of constructing new inferred inequalities based on a fixed set of inference rules. For each newly constructed inequality, we are going to store its cause vector, which describes how it was formed from the already existing inequalities. When a contradiction is found, we are able to construct a certificate of infeasibility by tracking the newly generated inequalities back to the original system and composing the cause vectors. As a simple example, consider the system of 5 inequalities which is in the diagram on the left. From the second and third inequality, we infer the new sixth inequality as a weighted sum with coefficients 2 and 1, which defines its cause vector. Similarly, we can combine the first and sixth inequality to obtain the seventh inequality by a weighted sum. We can continue deriving other inequalities until, eventually, we derive the 10th inequality, which is clearly contradictory. Its cause vector y10 therefore certifies infeasibility of the original system. Note that the cause vectors encode how each new inequality can be obtained from the original system. However, see that we constructed the new inequalities not only from the original ones, but also from the previously constructed inequalities. In our example, construction of each cause vector is done by explicitly storing all previously created cause vectors, but this is inefficient and not necessary in practice. In the paper, we described a general dynamic programming procedure which may utilize the sparsity pattern of simple inference rules to save memory and construct a cause vector efficiently only when a contradiction is found. We will now recall the binary weighted CSP and describe how virtual R consistency algorithm is subsumed by the previously introduced procedure. In binary weighted CSP, we are given an undirected graph where the nodes correspond to variables and edges to pairwise factors. We are also given a finite domain D and weights C. The task is to find a labeling from the set of nodes to the set of labels, which maximizes expression 3. This optimization problem has a natural LP relaxation, which can be expressed as the left-hand system in equation 4. On the right, we wrote the dual LP. If the conditions on line 4b in the primal are written explicitly, we obtain equation 5. To better understand this formulation, let us consider a graph with two nodes, one edge between them, and a domain with three labels a, b, and c. In the relaxation, there is a variable for each node label pair and also for each edge and pair of labels. In the shown diagram, only some edge variables are indicated for better readability. Since x empty set equals to 1 by condition 4c, condition 5b assures that for each node exactly one label is chosen. Conditions 5a are called marginalization constraints, which ensure that if, for example, node 2 is assigned label a, which means that x to a equals 1, then the highlighted edge variables need to sum up to 1. That is, one of them needs to be chosen. These constraints also exist for the first node. So if we also assign x1b equal to 1, then also the green highlighted edge variable is forced to 1. Of course, there also exist fractional feasible solutions. We remark that optimizing the dual LP can be seen as minimizing an upper bound on the optimal value of the weighted CSP by equivalent transformations of the weights. Assume that we are in a dual feasible solution YH. The corresponding complementary slackness conditions are given by the left-hand system 6, where the only difference to the constraints in the primal LP is that some of the variables are forced to be 0. In particular, JYH denotes the set of dual constraints active at the dual solution YH. In other words, J contains the indices of the active tuples. On the right, we wrote the Farkas alternative, which is feasible if and only if the left-hand system is infeasible. Any vector satisfying this system is a certificate of infeasibility of the left-hand system and constitutes and improving direction from the current solution. We remark that even though the system 6 are not in the form of Farkas lemma presented previously, there are many variants of the lemma, each suitable for a system of inequalities and equalities in different form. Recall that the conditions 6b correspond to condition 7. Let us now point our attention to the fact that left-hand system 6 can be also interpreted as an LP relaxation of a CSP where some labels and label pairs are forbidden by forcing the corresponding x variables to be 0. Consider the previously shown example with 2 nodes and 3 labels. In the figure on the left, we expressed the complementary slackness condition symbolically by stating which primal variables are forced to be 0 and which are allowed to be non-negative. Those variables that are forced to be 0 are highlighted in red. On the right, we have drawn the corresponding CSP where the allowed labels are filled and allowed pairs are drawn by black lines, whereas the forbidden labels are white and forbidden pairs are not drawn. Clearly, since the highlighted edge variables x are forced to be 0, the variable x2a also needs to be 0 by condition 7a. In the CSP, this corresponds to forbidding label a for the second node as it has no support. Let us now focus on the variable x2c, which is forced to be 0. Analogously, the 3 highlighted edge variables need to be 0 since they are non-negative and their sum must equal x2c due to constraint 7a. In the right-hand figure, this corresponds to forbidding the outgoing pairs from the label c in the second node. Clearly, we could continue analogously to the well-known R consistency algorithm, except that we would apply it on the continuous variables x. In the previous example, we have shown 2 propagation rules which set some variables to be 0 if such assignment is forced by the constraints and other 0 variables. These rules are in the first 2 rows in this table, where we also give the corresponding cause vectors. There also exists a third rule, which is applied when all the labels in a single node are forbidden, that is, all variables in a single node are set to 0. Then the conditions are clearly infeasible and we can compose the previously created cause vectors into a certificate of infeasibility, satisfying the previously shown Farkas alternative system. The derivation of the cause vectors is technical and proof of correctness is given in the paper. To see how this is subsumed by the previously introduced approach, the algorithm can be initialized in an arbitrary dual feasible point, which is easy to obtain. Then we apply the shown propagation rules on the complementary slackness system, which corresponds to an LP relaxation of a CSP. If domain wipeout occurs, which means that the R consistency closure is empty, the problem is infeasible, and we construct an improving direction as shown previously and update the current point. If the R consistency closure is non-empty, then the system is suspected of being feasible, we attained a fixed point, and the resulting instance is so-called virtual R consistent. The current dual objective provides an upper bound on the optimal value of not only the LP, but also the original weighted CSP instance. It is easy to see that the fixed points of this algorithm are the same as for WAC algorithm, but we observed that the improving direction may differ from the one which is constructed in WAC. Now we will move to the case of weighted WAC set. This problem is defined by a set of clauses where each clause is assigned a positive weight, and the task is to find an assignment for Boolean variables that maximizes the sum of weights of satisfied clauses. The LP relaxation of this problem is given in equation 8, where the variables z are indicators for which of the clauses are satisfied. Dual LP can be conveniently expressed as minimization of a convex piecewise affine function with non-negative variables. We will now apply the proposed approach on this Primal-Dual pair. Even though the dual is not expressed directly as an LP, eliminating some of its variables simplifies the reasoning. Assume that we are in a dual feasible point y, and construct the complementary slackness conditions. After a simplification, these conditions correspond to system 10, where the indexes C and X correspond to partitions of the set of clauses C and set of variables V given by Y. The conditions 10a to 10c express that at least one, exactly one, and at most one literal, in the clause needs to be satisfied. Condition 10d says that none of the literals in the clause may be satisfied. Also, some variables are set to 0 or 1 and some are undecided. Surprisingly, the conditions do not correspond to an LP relaxation of SAT, but to an LP relaxation of a Boolean CSP, and our proposed propagation rules correspond to enforcing its arc consistency. In detail, they set some of the undecided variables to have value 0 or 1 if such value is forced by some constraint. For example, in equation 10c, if one of the terms evaluates to 1, then all the other variables need to be set so that they evaluate to 0. And if in equation 10c there are two terms that evaluate to 1, we obtain a contradiction. There are 6 propagation rules in total, which we show in this table along with the cause vectors and to which sets of constraints is each rule applicable. Of course, whenever an x variable is set to some value, we need to store the corresponding cause vector so that if a contradiction is detected, we are able to construct a certificate of infeasibility. Even though the rules are simple, the derivation of equations for cause vectors and improving direction is non-trivial. We remark that it is possible to store the cause vectors efficiently with space complexity which is linear in the size of the input by using the structure of the bipartite closed variable graph of the instance. We proved that the fixed points of our algorithm are always global optima for instances of weighted max2SAT and for tractable subclasses of maxSAT defined by language and acyclic structure. For the instances where optimality was not guaranteed, we evaluated our algorithm using a public benchmark where we considered two criteria. First, criterion R compares the gap between obtaining bound by the algorithm and the LP optimum with the gap of a trivial bound given by the sum of all clause weights. Second, criterion Q measures the relative gap with respect to the optimal value of the LP. The figures below show the sorted values of the criteria with linear and logarithmic axes on instances where optimality is not guaranteed in theory. The comparison was performed only on those instances which could have been solved by a commercial LP solver without memory overflow. Our approach was able to approximately optimize all of them. To summarize, we have proposed a technique to compute bounds for sparse LPs with suitable structure. Having a feasible dual solution, infeasibility of the complementary slackness conditions is detected by constraint propagation, and the infeasibility certificate is recovered, providing a dual improving direction. This approach is memory efficient, which makes it suitable for large-scale problems. Additionally, this method generalizes the virtual arc consistency algorithm. The main purpose of soft local consistencies in weighted CSP is to bound the optimum value of weighted CSP during search. Each has a different trade-off point between bound tightness and computational complexity. In this view, our approach can be seen as a soft local consistency technique for other problems. Though in principle our approach can also be applied to other LPs if an initial dual feasible solution is available, the existence of good propagation rules and the quality of obtained bounds depends on the problem structure in a so far unknown way. It is yet to be seen if there are other classes of LPs where it would result in good upper bounds. But the package CSP is closely related to convergent message passing methods developed within computer vision, such as TRWS or maximum diffusion. Their fixed points are also characterized by a local consistency condition, and they can be seen as versions of block coordinate descent applied to the dual LP relaxation. This suggests there is a close connection between our approach and block coordinate descent methods. We clarify this connection in our second submission.